Okay, this is lecture number 15, EE313, Signals and Systems. So a preview of today's lecture. So I'm going to go through the Fourier Transform synthesis and analysis equations. So remember that in lecture number 14, I introduced the Fourier Transform as the limit of a Fourier series. Then second, we're going to look at the existence of the Fourier Transform, including the Dirichlet conditions. And then I'm going to show you how we can use the Dirac delta function to define transforms of signals that don't strictly satisfy the Dirichlet properties. And then finally, we're going to look at examples of calculating the Fourier transform and the inverse. So the relevant sections of Oppenheim and Wilsky are 4.1 and 4.2. Okay, first, an introduction to the Fourier transform. So the Fourier transform of a signal x of t, we write it as x of j omega, and we write in shorthand calligraphic f parentheses x of t. The Fourier transform of that function is another function, which is the integral from minus infinity to infinity x of t e to the minus j omega t dt. So the j omega here is so that we remember that there's a j omega in the exponential. And we're going to see that this is generalized when we talk about the Laplace transform. And then something to note is that this book uses j omega, but you also see in other books the use of omega instead of j omega. It means the same thing, it's just a notational issue. So let's look at how do we interpret the Fourier transform. So the Fourier transform is this integral of the product of x of t and e to the minus j omega of t. Well, remember from the discussion in a few lectures ago that this integral, you can think about this as an inner product between two signals, x of t and e to the j omega t. And we have no negative here because this is conjugated in the inner product. And so essentially what this is measuring is how much the signal x of t aligns with e to the j omega t. And so effectively, how much does x of t look like complex sinusoid e to the j omega t with frequency omega? So that's literally what the Fourier transform is. So if you evaluate x of j omega for a particular value of omega, that tells you how much in terms of amplitude and phase is that signal is related to e to the j omega t. So why do we care about complex sinusoids? Well, you should already appreciate that if we take a complex sinusoid e to the j omega naught of t, and we put it into a LTI system that has frequency response h of j omega, then the output is h of j omega times e to the j omega t. And so why you should care about this is that the convolution operation doesn't have to be performed, because all you have to do is multiply the input signal by its frequency response at the output if it's a complex sinusoid. So this is a very special case here. Now, if the signal can be represented as a sum of sinusoids, then it's possible to compute the output basically without convolutions. That's the point. And then remember that h of j omega here is the integral from minus infinity to infinity h of t e to the minus j omega t is the Fourier transform. So we've already seen this integral, but now we're seeing it and properly defining it as the Fourier transform. Okay, let's look at a first example. Let's consider the unit impulse function, so our Dirac delta, best friend so far. And if you see the Dirac delta here is this plot in the time domain, let's compute its Fourier transform. So we first substitute that into the definition, and then remembering the shifting property, so we can rewrite this delta e to the minus j omega t as delta of t e to the minus j omega times 0 dt. This evaluates to 1, so that's just the integral of the delta function, which is a 1. So an impulse in the time domain is a constant in the frequency domain. And so if you think about here the intuition, so the time domain signal is applied instantaneously, and that creates in the frequency domain something that has components basically of every frequency. So the more impulsive something is in time, the broader its spectrum in general in frequency. And we'll see this as a theme in several different examples next. Now let's compute another example. This one is a little bit more tedious, but I wanted to show it to you just to avoid doing too many simple ones. So let's compute the Fourier transform of this triangle function. So it's 0 everywhere except for in the range of 0 to 1 where it's 1 minus t. So let's go through here, substitute in for x of t, 1 minus t, and we integrate only on the region from 0 to 1. And now splitting up the integral, this becomes the integral from 0 to 1 e to the minus j omega t, which we've dealt with a lot. But we've also got another integral from 0 to 1 t e to the minus j omega t. And so here we're going to have to use integration by parts. So now let's look at that. So this is the first part. Using integration by parts on the second term, we get minus t 1 over minus j omega e to the minus j omega t evaluated at 0 and 1, and the integral from 0 to 1 minus j omega e to the minus j omega t, which becomes, with some more math, j omega squared e to the minus j omega t. So we get the j's cancel, so that becomes minus omega j omega plus 1 over omega squared. Evaluating this integral and simplifying, we get 1 over j omega minus 1 over omega squared e to the minus j omega plus 1 over omega squared. And so this is a non-trivial example of a Fourier transform. And I just wanted to show this to you because for the most part, doing a Fourier transform is really just about evaluating an integral. And so you just need to remember the basic rules of calculus in order to do that integration. Now let's look at the inverse Fourier transform. So the inverse, as we saw in the last lecture, is defined as 1 over 2 pi, the integral from minus infinity to infinity, x of j omega e to the j omega t d omega. Now note that this looks very much like the Fourier transform, except that the sign of the exponential here isn't negative, it's positive. And we have a scaling factor of 1 over 2 pi. So the scaling factor results because we're using radians in frequency, and I'll tell you later how the equation looks different if we don't use radians. And then we're integrating here because what we're doing here is summing up the contributions of different sinusoids instead of asking what is the contribution of a sinusoid in my signal. So just like the Fourier series synthesis equation, we have a positive frequency here. Now the fact that the Fourier transform and its inverse are very similar looking is going to lead to an important concept in signal processing called duality. And that's going to allow us to define the transform. If we know the transform of a signal from the time to the frequency domain, if we flip the signals around, it'll give us the transforms from frequency to time if we swap the indices. And I will explain that more in the next lecture. So now let's look at another example where we have a unit impulse in frequency. So our x of j omega is equal to delta of omega. So its Fourier transform is given by integral from 1 over 2 pi, integral from minus infinity to infinity, delta of j omega. So computing that, again, the same logic as before, we get 1 over 2 pi. So here what we see is that a delta in frequency is a constant signal in time. So a signal that is an everlasting constant in time becomes a delta in frequency. And the duality here is that before we had a delta in time and a constant in frequency. And now we have a delta in frequency and a constant in time. And the only difference between those two equations is there's a factor of 1 over 2 pi that comes when we're going from frequency, delta in radians into time domain. So this is an example of duality. Okay, so now let's start to look at manipulating some of the signals that we've already computed the Fourier transform of. So let's suppose that we have a shifted delta. Well, let's look at its inverse Fourier transform. So I substitute in for the delta function, and then using the sifting property, we can realize that this is only valid for e to the j omega naught t. So we pull the e to the j omega naught t out. We're left with the integral of the delta, which is just a 1. So the inverse Fourier transform is given by e to the j omega naught t over 2 pi. And we're going to see that in general, when you shift a signal in the time domain, you get a product of the form e to the j omega naught t. Sorry, this is a shift in the frequency domain. If you shift in frequency, this corresponds to what we call a phase rolling effect in the time domain. Now let's look at another example here. So this is one that I pulled from the Oppenheim-Wilsky book. So use the Fourier transform synthesis equation to determine the inverse Fourier transform of 2 pi delta omega plus pi delta omega minus 4 pi plus pi delta omega plus 4 pi. So substituting into the equation and separating out the integral and using the delta property, we get 2 pi e to the j 0t, pi e to the j 4 pi t, and pi e to the minus j 4 pi t. And getting rid of the 0 here, this becomes, and multiplying through by 1 over 2 pi, this becomes 1 plus 1 half e to the j 4 pi t plus 1 half e to the minus j 4 pi t. Now we can combine those two together using Euler's to get 1 plus cosine of 4 pi t. So here, note that we had 3 impulses, and 2 of the impulses were at reciprocal frequencies. So these two combined into a cosine, and this one came from a constant. So there's a lot of similarity here between this example and what we saw with the Fourier series. And we're going to exploit that in the next section. So to summarize here, the Fourier transform analysis equation is the integral from minus infinity to infinity x of t e to the minus j omega t. So we're analyzing a signal, we're determining the frequency content of a signal. The inverse Fourier transform is the synthesis equation, and here we are synthesizing a signal by taking sums of exponentials. And then we say that x of t and x of j omega are related by the Fourier transform. We use this little double arrow here. So this says that x of t has a Fourier transform x of j omega, and x of j omega has inverse Fourier transform x of t. Now, I want to also present an alternative formulation of the Fourier transform, where instead of using omega and radians, we use a frequency variable in Hertz. And so if we write it in frequency, Fourier transform will be written as a function of f, and it would be minus j 2 pi f instead of omega. And then the inverse Fourier transform is the integral from minus infinity to infinity x of f e to the j 2 pi ft. So the nice thing about using Hertz is that you get this very symmetric equation. There's no 1 over 2 pi floating around. And so if you take my class on wireless communications, 471C, we'll actually use the Hertz formulation. In DSP textbooks, you see the use of both Hertz and radians. In communications, we tend to see examples more in Hertz. So we're going to focus on using radians, though, in 313, using x of j omega as we exploit in the Oppenheim-Wilsky book. Okay, so now let's talk about the existence of the Fourier transform. So the question of this section to answer is, when does a Fourier transform exist for a given signal? So if a signal is what's called finite energy, which means that if you integrate the magnitude squared of the signal and it's less than infinity, then the Fourier transform exists. And further, there is zero energy in the error in the sense that x of t minus the integral minus infinity to infinity x of j omega e to the j omega t is 0. So this is called the mean squared reconstruction error is 0. And so most of the signals we consider in class are of this form where they have finite energy, and so you can basically just take the Fourier transform and you'll get a well-behaved signal and its inverse. Now, so that's what's called the sufficient condition for the Fourier transform to exist. Another condition is the Dirichlet conditions. And this says that if the signal is absolutely integrable, so notice we don't have the square here. If we can integrate it from minus infinity to infinity x of t dt, and it's finite, and it has a finite number of minima and maxima over a finite interval, and a finite number of discontinuities over a finite interval, then x of t and the inverse Fourier transform of 1 over 2 pi integral from e to j omega t are equal except at any point of discontinuity. And so the signals more generally that are not finite energy signals will satisfy this property here. And so the important thing to note is that for most signals, these two are exactly equal. And if it's only satisfy the Dirichlet conditions, then they're going to be equal except at a point of discontinuity. And then if they satisfy the finite energy property, then the error in that integral is zero. So these are rather technical conditions, but it is good to know that both of these sufficient conditions, the finite energy and the Dirichlet conditions. Now, an important class of signals whose transforms we want are periodic. So we've already been studying periodic signals extensively for the Fourier series. But the problem is that they don't satisfy either sufficient condition because the integral of the energy squared is infinity because it's a periodic signal, and the integral of the absolute value is infinity because it's a periodic signal. So if we can use the Dirac delta function, though, we can define the Fourier transform from the Fourier series. So suppose I have a periodic signal with Fourier series coefficients a of k. Then the Fourier transform I define as x of j omega, which is the sum from minus infinity to infinity, 2 pi, a sub k, delta omega minus k omega naught. So here's the Fourier series coefficients. 2 pi is a scaling factor we need just because we're working in radians. And then we get delta functions at multiples of k times omega naught. And so this is what we would call the Fourier transform of a periodic signal. So you should definitely know this equation. Now let's look at an example here. So what we say is that periodic signals have a line spectrum. And so by line spectrum, I mean that the Fourier transform looks like a whole bunch of lines. Also, this is called a comb spectrum. The deltas occur at multiples of the frequency omega naught. So you have a delta at 0, omega naught, 2 omega naught, 3 omega naught, and so on, minus omega naught, minus 2 omega naught, minus 3, and so on. So all of the harmonics have a delta, and the amplitude of the delta is exactly 2 pi times the Fourier series coefficient a of k. So if you have to find the Fourier transform of a periodic signal, you first find the Fourier series coefficients, and then you use this equation to find its transform. Okay, so now let's look at an example, the shifted delta and frequency again. So consider the signal x of t is 1 over 2 pi e to the j omega t. Well, the signal is periodic with fundamental frequency omega, so it has a Fourier series expansion given by the sum from minus infinity to infinity, a of k e to the j k omega naught t. And of course, in this example, there's only one non-zero coefficient, which is a1 of 1 over 2 pi. And so using the equation on the previous slide, we can conclude that 1 over 2 pi e to the j omega naught t has Fourier series coefficients delta of omega minus omega naught. And generally, if instead we were to look at e to the j omega t, that has Fourier transform 2 pi delta omega minus omega naught. So shifted delta scaled by 1 over 2 pi gives us a delta. So the shifted the scaled time domain complex sinusoid gives us a delta, and the unscaled complex sinusoid gives us 2 pi times a delta. So all we're doing here is using this equation right here that I mentioned is very important. Okay, so now let's look at some Fourier transform examples. So first let's consider the causal exponential function. X of t equals e to the minus at u of t, where the real part of a is greater than 0. So it's Fourier transform, so we substitute in x of t, integrate, get rid of the unit step function. We're integrating from 0 to infinity, e to the minus at, e to the minus j omega t. So collecting the arguments of the exponential together, we get e to the minus a plus j omega t here. So now this is standard calculus. Integrating that, we get minus 1 over a plus j omega, evaluated e to the minus a plus j omega at 0 infinity, which is just 1 over a plus j omega. Let's look at another example here, cosine. So this is a periodic signal, so we can find its Fourier transform using the Fourier series. We decompose it into, using Euler's, into complex sinusoids. 1/2 e to the j omega t, e to the minus j omega t. And then leveraging the frequency impulse response results, we can write this as 1/2 of 2 pi delta omega minus omega naught plus 2 pi delta omega plus omega naught, which is going to give us the pi at delta of omega plus omega naught and delta omega minus omega naught. So the cosine has two impulses in the frequency domain. Now let's look at the Fourier transform of a sine. So consider the signal x of t is equal to sine of omega t. To get its Fourier transform, we decompose in using Euler's identity, 1 over 2j e to the j omega naught t minus e to the minus j omega naught t. And then writing this in the frequency domain using the results from the connection between the Fourier series and the Fourier transform. This is 1 over 2j, 2 pi delta omega minus omega naught minus 2 pi delta omega plus omega naught. And we can rewrite that by getting rid of the multiplying through by 1/2 and putting the j in the numerator as pi j delta omega plus omega naught minus delta omega minus omega naught. And then in the frequency domain, we would write this as follows, where there's a typo here. There should actually be a j associated with the amplitudes here. All right, now let's look at the Fourier transform of an important function, which is the rectangle, the rect, that we've seen now in several examples in the course. So remember that the rectangle function is a rectangle from minus 1/2 to 1/2, 0 everywhere else, and it has an amplitude of 1 in that interval. So note that if you integrate x of t, that integrates out to 1. Now you can create other rectangles from this basic rectangle by scaling. So if I scale by a, I can change the amplitude. And if I divide by b, I change the cutoff. So t over b gives us a cutoff of b over 2. And a rect of tb gives me a cutoff of 1 over 2b. So we're going to start off by analyzing the basic rectangle, and then we'll consider other special cases. So let's look at the Fourier transform of the rectangle function. So the Fourier transform is given by the integral from minus infinity to infinity of the rectangle. Now, using the fact that it is non-zero only from minus 1/2 to 1/2, we get e to the minus integral from e to the minus j omega t dt. Evaluating that integral gives us minus 1 over 2 j omega, e to the minus j omega over 2 minus e to the j omega over 2. Now you can stop here, but this actually simplifies even further. So if we pull out a 2 omegas, we put the 2 here, we separate the j and omega. This looks like a sine. So we can write this as 2 omega sine of omega over 2. Or sine of omega over 2 over omega 2, which is just the sinc of omega over 2 pi, based on how we defined the sinc function. So the Fourier transform of a rectangle is a frequency scaled sinc function. Now I want to say a little bit about this sinc function here. The way we define it in class, the sinc is the sine of pi t over pi t. This is a plot of the sinc here. So its maximum value occurs at t equals 0, which is 1. And it has 0 crossings at 1, plus minus 1, plus minus 2, etc. here. So note that all the zeros, 1, minus 2, minus 3. And this makes sense because at this point 1, you have the sine of pi over pi. The sine of pi is 0. And here the sine of pi at 2 is 0, and at 3 is 0, and at 4 is 0, and so on. But we showed in an earlier lecture that the limit of the sinc function as t goes to 0 actually is 1. So this is the sinc. It goes off to infinity here, and this is a common function that we're going to use quite a bit in the course. Now let's plot the Fourier transform of a rectangle function. So the Fourier transform of the rectangle function we said was the sinc of omega over 2 pi. So plotting this here gives us a function that looks the same, except now the zero crossings are at plus minus 2 pi, plus minus 4 pi, etc. So dividing by 2 pi just changes the zero crossings into multiples of crossings at multiples of 2 pi. So we just did the Fourier transform of a sinc. Now let's do the Fourier transform of a scaled rectangle function. So we're going to scale the rectangle from minus t1 to t1 now. And this is very similar to one of the examples that we did earlier with the Fourier series. So we can write this as the rect of 2t over 2t1. And then we're going to integrate from minus infinity to infinity. So this is just the integral from minus t1 to t1 of e to the j omega t dt, which is the integral from minus 1 over j omega e to minus j omega t evaluated at minus t1 and t1. So we get something that looks very similar to what we just did, except that we end up with a t1 here in the sine function. And so we can rewrite this as a sinc. We multiply and divide by t1, and we're left with t1 sinc of omega t1 over 2 pi. So the scaling, dividing by t1 here, has the effect of multiplying by t1, the frequency by t1. Okay, so to summarize, the Fourier transform of a rectangle function from minus t1 to t1 is the sinc of omega t1 over 2 pi times t1. So the amplitude gets scaled by t1, and the crossings are reduced by t1. And so what happens is as the pulse gets narrower, so t1 shrinks, the sinc becomes wider. And as t1 increases, the sinc becomes narrow. So what happens is, so if you send something like a very, very sharp pulse, that has a lot of frequency content. And a very broad pulse has less frequency content. So that's summarized here. Narrow pulse in time is broad in frequency, and vice versa. Okay, so now let's compute the Fourier transform, the inverse Fourier transform of a rectangle function. So suppose we have rect of omega over b. So that b here is the cutoffs of the rectangle function becomes b over 2 and minus b over 2. We're using the term b here because later we'll talk about the extent of this in frequency as being the bandwidth. So plugging in and taking the inverse Fourier transforms, we have a different sign here. Going through the same steps as the previous example, we end up with b over 2 pi sinc of bt over 2 pi. So a rectangle in frequency becomes a sinc function in the time domain. The amplitude is b over 2 pi, and the crossings occur at 2 pi over b, 4 pi over b, etc. And so this is an example of duality where a rectangle in one domain is a sinc in the other domain. And so that's previewed right here, the concept of duality. So rectangle becomes sinc, sinc becomes rectangle. And note that we've scaled the rectangle functions differently, and that leads to different behavior of the scaling of the sinc. Like here we have b over 2, so we get crossings at 2 pi over b. Here we had t1, so we get crossings at pi over t1. And this concept of duality will be very important because if you know the transform from the rectangle to sinc, then it means that you also know the transform from sinc, which is a rectangle. And so we'll talk more about the exact scaling of duality in the next lecture. So to summarize the lecture, so Fourier transform is a generalization of Fourier series to almost an arbitrary signals. It applies to aperiodic signals. Now, the Fourier transform can't be computed for every possible signal, but there are special cases of signals that work, so finite energy signals and signals that satisfy the Dirichlet conditions. We can also define a Fourier series of a periodic function the Fourier transform of a periodic function by using the Fourier series. And periodic functions have a line spectrum in the Fourier domain. And then finally, we did some examples with calculating the Fourier transform of the inverse. And so you should be able to use the analysis and synthesis equations. Basically, it's an integration problem. And then, as we'll see, we did some examples of transforms of special functions like the exponential step function, the delta, the shifted delta, the rectangle, and the sinc. Now, what we're going to do in the next lecture is we're going to use the properties of the Fourier transform to simplify the calculations. So this is going to be just like we did with the Fourier series, but we're going to do it now with the Fourier transform, things like linearity, shift, multiplication, convolution, and so on. So that's what you have to look forward to.